Well, just like force is what causes translational motion, torque is what causes rotational motion. And although we're not going to carry these thoughts too far in this course, I want to introduce you to just a little bit of what it takes to cause rotation or twisting forces. So a mass has inertia, resistance to any kind of change in motion, as we know. It also has a moment of inertia, which is a measure of how hard it resists a change in rotation, just like inertia and translation. So they're very similar. It's a very good analogy. Now, anything that's either not rotating or whatever the state of affairs is, it might be rotating already. It requires a twisting force to change that state of rotation. All right. And that operation is what's called torque. Now, the moment of inertia, very similar to inertia, but the moment of inertia, symbol I, is based on the distribution of mass in the object itself. It turns out if the mass is distributed further from the axis of rotation, the moment of inertia goes up a lot, even if the mass stays the same. All right. There are three things that affect this thing we call torque in terms of how we apply it. So it depends on force, it depends on the radius arm, and it depends on the angle between those two items. So here is a quick example situation. Here we have a bar that's pivoting about this point, and there's three forces, all the same size, acting at different locations. So the question is, which one produces the greatest torque? And by common sense, it's going to be F3, because your, hopefully, common sense informs you that when you want to twist something, it's easier to do it further away from the pivot point. So this has a longer radius arm then, about which the force is acting, and it makes it easier to twist it or rotate it, give it angular acceleration. If you put a wrench on an object, if here's the nut or bolt, and this is the arm of the wrench, you tend to grab it at the end to put the most twisting force on that object. All right. The next situation is where we have three forces of different sizes acting at one point. It's meant to be acting at the end here. Okay? And we see that F1 is going to produce the largest twisting force because the force is the largest. Very simple. And the final variable here is if we put three forces of the same size at different angles. Well, if this is looking down on a door, if you push the door open this way, you know that works. How about in this direction? If you do it at an angle, you probably can sense that it's going to be harder. If you push, this is a top view of the door now. If you push against the door into the hinge, you're not going to get much action, are you? So F1 is the correct answer, since the angle that the radius arm makes with the force is most perpendicular. So those are the characteristics. So we can put all this together. I'm going to use the symbol cap gamma for torque, and it's the perpendicular force times the radius arm, or the force times the perpendicular radius arm to that force. Both mean the same thing, essentially. So here we have a pivoted arm, just like we had the radius, and we're going to apply a force given by this at an angle theta. Now, what does the parallel part of that force do? Here's the force, the parallel part of that force. Well, it doesn't do anything in terms of rotating the object. So it's the perpendicular part. So what part is perpendicular? Well, we have this theta, which is the angle between the radius arm and the force. So it's the vertical component, and you probably can see that's the sine times the actual size of the force. So force sine of theta gives you the amount of force perpendicular. So putting this all together, we now see that torque is going to be the product of the radius and the perpendicular part of the force which is RF sine of theta. And that's a brief overview of this thing we call torque, the cause of rotation.